Вам принципиально важен габилитет или нет?
Нет, принципиально.
У нас есть, значит, один не...
Окей.
Но мы будем вопрос по-русски задавать. У нас так принято, что
Отвечать матом.
Okay, so thanks for the invitation, first of all, to give a talk here. So I'd like to thank Alexei and others involved for the invitation. Okay, so I'll be speaking about some activity related to two-dimensional sigma models that I've been involved in the past few years. I'll first of all give some, maybe a little bit of backup or background where it kind of comes from. Two-dimensional sigma models. So this means these are some theories related to maps of some two-dimensional manifold, some target space M. Yes, this will be a Riemann surface in our application. So they have been investigated from the point of view of integrability since the 70s, maybe. So in particular, well, maybe the pioneering works or in this direction were Paul Meyer, Zakharov, Mikhailov.
The dimension of M is any.
Yeah. Well, I mean, of course, we will be dealing with some concrete models that I will specify later. Etc. So they constructed so-called zero curvature representations for these, for the equations of motion of these models, which were, which underlie the integrability structures in these models. So they construct some zero curvature representations. So there's some story related to integrability of these models. Somehow, actually my talk today will not really involve much of integrability, so maybe I will not dwell into this story too much, although in principle the idea of, or the goal of this program in general is to investigate the integrable properties or maybe to solve these models in the future. But for the moment I will just present a different way of kind of new variables for these models that I think are useful even in perturbation theory. So for example, these variables allow constructing a well-defined perturbation theory.
So maybe it should be somehow specified. What is the manifold, the target manifold?
Yeah, sure.
And when you speak about this by integrability, as I understand, you mean classical integrability, yeah?
Yeah, this was classical integrability. Later on, it was promoted to quantum integrability by Zamolodchikov and Zamolodchikov, others. So there's both classical and quantum integrability. In principle, I will towards that.
Выключить?
Не знаю, было.
Ну, я просто знаю, там просто ремонт какой-то. Давай.
Ну, ремонт не так был.
То есть ремонт тебе тише, да?
Yeah, but by the way, I have 1.5 hours, right? Okay. So yeah, towards the end of the talk, I will pass over to the quantum theory. So of course, the idea is that one should be able to study quantum theory using these new variables, and these new variables are useful in the quantum theory. So I will at least consider the path integral, yes, I will specify what the target spaces are. But the point is that so for these elementary constructions of the zero curvature representations or for some simple hints that integrability should hold, the important property was that the target space should be a symmetric space. So this M was a symmetric space in this classical work, and most of them were.
Small question, is it Alexander Mikhailov, the author of the
Yeah, I think so, yes. Okay. So M will always be a homogeneous space also in my talk. In this old work, it was a symmetric space. So symmetric space is a particular class of homogeneous spaces. There's some technical definition. For example, spheres are symmetric spaces. Say Riemannians, GPM, etc.
Complex groups.
Yeah, these are homogeneous spaces of compact groups, yes, if that's the question. Okay, so, yes, G is semi-simple or compact, or maybe it can involve U1 factors as usual. But the point is that, yeah, so symmetric spaces and so on, but for example, flag manifolds, general flag manifolds, F of, let's call D1, D2, etc. And some embedded spaces. They're not symmetric spaces. So at some point I got interested in flag manifold sigma models. These are flag manifolds of the unitary group. Yeah, so I showed that in this case it's also possible to construct some models which admit zero curvature representations and which are therefore candidates for integrable models. So this was my work from 2014. Then the question was, what is the full class of theories that admit these zero curvature representations that are kind of beyond these classical results? And then another result was that actually for the zero curvature representation to hold, the target space should be a complex homogeneous space. It should be a target space complex. So somehow the complex structure was crucial. So this was 2016. And then there was an important.
Is sufficient condition or what?
Yeah, it's a sufficient condition. Yeah.
Because not all your spaces are complex.
Yeah, sure. It's a separate class of spaces. There is some non-zero intersection, but it's yeah. But somehow the claim is that for these spaces things are nicer than in general, much nicer. So yeah. So then there was an important work of Costello and Yamazaki in 2019, which showed that maybe the important thing is not just that, perhaps not that the target space is complex homogeneous space, but rather that the phase space is a complex symplectic. Complex symplectic. So this is Costello and Yamazaki. So in particular, these models from the previous points, they fall in this class also because the corresponding complex symplectic, well, so I can pass here by considering T star. This is the phase space. The phase space is the cotangent bundle to the target space. And these are effectively these homogeneous, complex homogeneous spaces are effectively flag manifolds. So there are quotients of some complex group by parabolic subgroup. So Then you consider their cotangent bundle. This is a complex symplectic manifold. And then yeah, so then this idea of complex symplectic manifolds plus so phase space plus what is called GLSL, so gauge linear sigma model. Sigma model, this gauge linear sigma model approach, this leads naturally to these complex symplectic manifolds being quiver varieties. Quiver varieties. And in particular, actually, what I will need is really not complex, not the resolved complex symplectic manifolds such as cotangent bundles, but really I need something smaller, which are the nilpotent orbits of complex groups. So nilpotent orbits. So these also carry a complex symplectic form, like any orbit. And this will be the phase spaces of my models. These nilpotent orbits will be the phase spaces of my models. And these cotangent bundles can be seen as the resolutions of these nilpotent orbits, but I actually don't need the resolutions. And the nice thing that it's actually nice that I don't need resolutions, because it's known that nilpotent orbits, at least of the classical groups, are quiver varieties. So far it has been done for kind of SLN, SON, SP2N. So for the case of SLN, and this will be, the quiver varieties give very useful variables that actually are well defined in quantum theory. And in physics language, this is what is called Gross-Neveu models. Generalized. So for the case of SLN, this one shown by Nakajima, 94. And for these groups, it was Kobak and Swan, 96. So at least to this, this machinery can be applied to, in principle, to flag manifolds of these groups, therefore. And the claim is that these models can be recast as Gross-Neveu models, generalized Gross-Neveu models.
Machinery, what is your aim? So what is your final? What would you like to construct for these sigma models? What's the representation of what?
Well, yeah. Well, in principle, I would like to construct a quantum solution. So kind of quantum transfer matrix and so on to diagonalize it and stuff like that. But for now, yes, there are classical Lux pairs, classical zero curvature representations, and there is a well-defined perturbation theory in quantum theory that is still useful. So in general, sigma models do not have a very good perturbation theory. I mean, the perturbation theory that people usually use is the 1 over n expansion. But this gives a perturbation theory for any n, well-defined perturbation theory.
When you say perturbation theory, perturbation with respect to which parameter?
Well, the curvature. So I mean the 1 over radius of the target space. Yes. So this gives a well-defined perturbation theory. Already this is useful. There are various questions that already arise at this stage. So I will kind of restrict to this. But in principle, yes, it should be. So the Lux pairs that are obtained in this way are what is called ultra-local Lux pairs. So they're nicer than the. So they're like mechanics, Lux pairs in mechanics. So they should be probably amenable to quantization. But this has not yet been done. So Okay, and then there is some generalizations of this. In particular, there is one can construct deformations, kind of canonical deformations, but there also admit a classical Lux pair deformations. Then one can consider the supersymmetric case. And this gives an alternative kind of target space construction of world-sheet supersymmetry, so to speak. Hopefully I will have time to explain.
Almost no chance, but maybe you can at least explain something on some simplest possible example.
Yes, which will be the CPN model. Yes, I will now pass to CPN model, which is the simplest example. This is just an outline kind of. And then you can, in principle, generalize the formalism allows to generalize naturally to Riemann surface worldsheets. So at least the theory is seems to be defined on an arbitrary Riemann surface, and whether integrability holds there somehow, that's a kind of open question. Okay, so now I will just start from the CPN model. How do you erase here? Oh, we'll do this. Yes. Yeah, there used to be some tablets where you rotate something and it erases the screen. Okay, maybe I will not start from the CPN model. I will start with some more general stuff, but it will naturally lead to CPN model. Okay, so at the point we can actually start from a even more well-known model, which is the principal Cairo model. So at least classically, some of this stuff is applicable to the principal Cairo model. So this is by definition the case when the target space M is a group G, such as SUM. Let's assume it's SUM. SUM. Yeah.
More nice is only SU2.
Yeah, then you define what is called a Maurer-Cartan current usually. So by bar I mean Hermitian conjugation. And then by construction this satisfies a zero curvature equation. And then there's an equation of motion of the model which says that d star j is 0. So this star is a Hodge star. It acts on dz multiplies dz by I and dz bar by minus I. But the point is that these two equations can be compactly written as d bar jz equals I commutator of jz bar. And one nice consequence of this equation is that we have conserved quantities which are traces of powers 0, 1, 2, etc. Homomorphic conservation laws. And now we will say that we restrict to the case when the worldsheet is a sphere. In this case, this says that these are holomorphic sections of powers of the canonical bundle over the sphere, and there are no non-zero such sections. Therefore, all of these holomorphic quantities are just 0. So this special case on a sphere is some kind of vanishing theorem on a sphere. So this has been used in the past extensively by Dean Zakharevsky, 1981, Fulenbeck. So the sphere is somehow a special case where things are particularly simple.
Sorry. So these cards, they take part in the algebra.
Yes.
Yeah. So for L equals to 1, it's obvious.
So, okay, yeah. Well, it could be UN, but
UN, I see, and then it is like total moment.
yeah. So, well, in physics language, you could just say that we're solving this with decay conditions at infinity. So this is a holomorphic function decaying at infinity. So as such, it is 0. So that's this is maybe a more fancy argument. So it means that traces of powers of this matrix are 0, which means that this matrix is nilpotent. So because its coefficients of its characteristic polynomial are polynomials in the traces.
For which n this is true?
For n, SUM, size of matrix. Well, it could be for a smaller n also, right? But at least, for sure, for n, yeah. In some situations, it could be for a smaller. So this is the first instance of why nilpotent orbits come about, because this JZ is not a Hermitian matrix. It lies in a SLN, the algebra. So it's a nilpotent matrix. It's an element of some nilpotent orbit of SLN C. And then, yeah, so what one can do is one can construct the, yeah, so, and the nice thing is that, of course, so the nilpotent orbit is defined by the Jordan type, by the Jordan type. And the nice property of this equation, the Jordan type of the nilpotent orbit can only change at points on the Riemann surface, at some points. It cannot change randomly from point to point. This is because this equation can be formally solved, at least locally, as JZ so some matrix G times a holomorphic matrix K.
It's another G. Not the same as
Yeah, not the same G, yes. And this matrix K is nilpotent, therefore. But it's a holomorphic matrix. So its Jordan type only changes at some points, because it means that some minors have to be 0, and these minors are some functions of Z. So they can only be 0 at some points, unless they are exactly 0. So this means that the Jordan type of this JZ only changes at some points. And actually one can show that one can uniquely continue this matrix into the points, so to speak. Even the points that these points do not matter where this matrix changes Jordan type.
You mean isolated points, right?
Isolated points, yes. So now to this matrix J, one can given such a matrix J, one can construct a flag. Yeah, the flag is Vm equals the kernel of JZ to the power m. Kernel of powers. This is a flag, so there is a Vm belongs to Vm plus 1. And yeah, so let's assume that Jz to the power n is 0 for a moment, but Jz to the power n minus 1 is not 0. Or else we have to consider a simpler situation. So this gives some flag. It's easy to show that given this condition, it's a complete flag. So there is a each of these kernels. It's a proper embedding. So there is a increase in the size of a flag by 1 at each step. So this means that at each point of the Riemann surface, ZZ bar, we have some complete flag in CM. Right? So this means we have a map from the Riemann surface to a flag manifold. Well, in this case, a complete flag.
It's still a sphere.
Yeah, it is still a sphere, yes. Well, on a sphere, this is necessarily so, right? If you have some other worldsheet, you could in principle impose this as an extra condition. So this would be on a sphere we derive this. These are the only harmonic maps on the sphere. All harmonic maps on the sphere satisfy this. But on other Riemann surfaces, this is a special
There
class.
are holomorphic differentials in principle, yeah, so that's why it's not necessary.
On higher genus Riemann surfaces, yes, sure. So yeah, let's assume this sphere. But now the point is that these maps are themselves.
Did you say that you assume the nilpotent always is the regular nilpotent always?
Yeah, so this is a regular nilpotent orbit. Yeah, that's right. This is a generic kind of nilpotent orbit.
Yeah.
Yes. They're also, you could consider, yes, that's right. So you could consider smaller nilpotent orbits, and this will give rise to partial flag manifolds as a result. So actually, it's an interesting case. So maybe the most interesting case is JZ squared equals 0, like you were asking. So this could as well happen, right? This is a particular degenerate situation, and in this case, the target space is a Gross-Neveu, GKM, where K is related to the number of Jordan blocks of size 2. Well, there are Jordan blocks of size 2 and 1, and there is a one-to-one relation between K and the number of these Jordan blocks. Yes. But the point is that in all of these cases, these maps are not some arbitrary maps, but they are themselves harmonic maps, meaning that these maps themselves are solutions of some sigma model. So maybe generalized harmonic maps. So in case of Grassmannians, these are literally the harmonic maps. In case of arbitrary flag manifolds, these are generalized harmonic maps, which I'll explain. From the point of view of sigma model, it means there's some B field.
So where from this harmonic maps come?
You mean how do I prove that it's a harmonic map?
How do you see them?
Yeah. So I will now do the reverse procedure. So now I will write a Lagrangian for these models, and then I will show that some quantities satisfy the principal chiral model equations, nilpotency, and so on. I guess. In principle, by just saying that those guys are in the kernel of JZ, you can write equations for the elements of the kernel and show that these are harmonic map equations. You could do that as well. But these are kind of these supposedly integrable models with like manifold target spaces that I will be talking about. Well, I will be talking about the CPM model, but like I say, it can be generalized. Yeah, so the nice thing is that these models have a nice Lagrangian description which can be used for quantization, construction of path integral, and so on. Maybe in passing, I also mentioned that this theory PCM, it also has a Lagrangian description, where the Lagrangian is just trace JZ bar. Here there is also a Lagrangian description, so you can derive these equations from the Lagrangian. We did not need it so far, but
second equation, d star g equals to 0.
Yeah, that's right. Yeah, so we use in Lagrangian, we use this already as a or you should impose this additional. Yes, but yeah, basically this is a solution of this equation. So
Yeah.
yeah, so this was just a general kind of discussion to motivate why such theories might or should exist. And now I will write explicit Lagrangians for these theories, which make it much easier to understand how it comes about. Okay, so we'll start from the CPN model, which is the simplest flag manifold, which is a model also well studied in the past and so on, but in a different formulation, which maybe is not that nice. Yeah, I'll start by saying that I'll start by introducing this Gross-Neveu model. So it's easier to work backward. So we'll write the Gross-Neveu model, then we prove it's equivalent to the sigma model, to the CPN sigma model. So I will write the following Lagrangian. So we have a Lagrangian, which is the sum psi a bar, psi a, kappa,
And your sigma 2 is now what?
sigma 3, yes?
I mean sigma 2. Sigma. The surface. Which one?
Sigma, well, for now we will just assume it's a complex plane. But
Sigma 1.
Okay, can be sigma 1, yes. Or C even, I mean, non-compact is allowed.
Казалось бы, Лагранжан ты можешь по любой поверхности интегрировать.
А вот, ну, хорошо.
Ну, нужна метрика, конечно, но
Вот, хорошо. Что ты видишь, или
ну,
нет?
по-моему, сфера или вот плоскость, да.
Ну, сфера-то годится, конечно.
Yeah, in principle, when you write a sigma model Lagrangian like this, we have, you see, it depends actually on conformal structure on the. If you write this with a worldsheet metric, you will see that the conformal class of the metric only enters. And conformal classes of metrics are in one-to-one correspondence with complex structures. So this is the same as picking complex coordinates here. This is why complex coordinate featured here. But yes, yeah. For now, let's assume that sigma is just C. Later, like I said, we discussed a little bit about Riemann surfaces and so on. Here, sigma 3 is a. So these are chiral projectors. So sigma 3 is a 0, 1, minus 1 polymetrics. So these are just projectors on top bottom components of this psi's. Psi are some are doublets. These are Dirac spinors in 2 dimensions. They are complex doublets. And as such, they can be written as psi a equals UA B A bar. A goes from 1 to n, yes. N will be SUM, SUM flavor index. SUM symmetry. And D cross D is a Dirac operator with respect to some gauge field, which you can think of as a U1 gauge field.
And psi bar is what? Is Dirac conjugation or Hermitian?
Hermitian conjugation, yes.
So bar is just
Yeah.
I mean bar. So, but it's Euclidean theory.
Yeah, that's always
And
Euclid.
that's
Yes.
why Euclid,
You don't have gamma zeros in front of it.
Yeah. Should be the same as
Yeah,
yes.
just ordinary.
Yes. Yes, so D is a U1. There is a U1 covariant derivative here. But actually, as we will see, it's actually can be thought of as a C star covariant derivative. So this theory has a C star gauge symmetry, despite appearances at first sight.
Can we make them explicitly, right? Because somebody probably don't know what this.
напишите.
Right, what?
Что такое C-star?
Не систер. Зачем ТД, что это такое?
И перечеркнуть.
Yeah, so D is D Dirac operator, which is a di sigma I. I goes from 1 to 2. So it's an operator of the following form. So there is some curly D bar. So the sigma i's are the gamma matrices in two dimensions. And this D is a D over dz plus or minus maybe okay, minus I A curly A. So this curly A is like A1 plus IA2 is a complex number, so to speak. It's complex gauge field. But it comes from just completely usual gauge field with from the two real components of the gauge field. They're combined as A1 plus IA2. And there in D bar there is accordingly D over dz bar and A bar. Okay, but the difference from the usual, so this is what is called the Gross-Neveu model. It's known since the 70s, again, maybe 1974, even earlier than the CPN model. But back in the days, people studied this as a fermionic model. So these psi's were anti-commuting variables. So here, instead, we will postulate that these are commuting variables. So these U and V are just bosonic fields, commuting bosonic fields. And now let's, and the claim is that this is equivalent to the CPN sigma model, explicitly equivalent. Let's see why that's the case. So now let's just write this Lagrangian in these U and V variables. So now it has the following form. So this is the Lagrangian. Okay. So now you can already see that it has a C star gauge symmetry. So there is a C star gauge symmetry. It acts by multiplying U by some function lambda and V by inverse of lambda. Where lambda belongs to C star. So lambda can be a function of z and z bar. So for every point on the surface, it belongs to C star. And the gauge field, so for this to be a gauge symmetry, the gauge field has to shift as follows. So lambda is a complex valued function, and here there are these covariant derivatives which make sure the transformation of U compensates against transformation of V. And this is also chosen in such a way that the two transformations cancel, right? This is due to the chiral projectors that were here. If you drop the chiral projections, you will also have terms of the form U to the fourth and V to the fourth, which are prohibited by chiral symmetry, and we don't want them, which will be clear by now why we don't want them. But it's actually rather non-trivial that this is a gauge symmetry, because we actually started with U1 kind of. U1, we introduced a U1 gauge field. But the point is that this theory is chiral, and in Euclidean signature, so there's some special thing that happens in Euclidean signature. So in Euclidean signature, chiral symmetry is the complexification of the non-chiral symmetry. So if you have the original star, I mean your charge symmetry, say U1, this becomes C star in Euclidean signature. So in Minkowski signature, this would become U1 times U1. But in Euclidean signature, it becomes C star. And if you have, say, SUN, it becomes SLN. And we actually do want this because ultimately.
U1 plus U1, you mean axial plus vector?
Yes. This is a joint. I mean, the U1 numbers of modulus 1, the U1, the usual U1 inside the C star.
So which of these two becomes nilpotent of axials?
The axial becomes
Axial
nilpotent,
becomes-
yes. I mean, you see, if you just take lambda as a phase,
Yeah.
this transforms as an opposite phase, but that means that the Dirac spinor just transforms by a phase. So this is the usual. And we want this C star because this C star is just the C star that enters the definition of projective space. So, I mean, CPN is. So Cn without 0 divided by C star, and this will be this C star. So we're gauging some chiral symmetry, which kind of we introduced a U1 gauge field, but it's automatically invariant with respect to C star. That's some property of this series. Of course, it might be subject to anomalies quantum mechanically, but this is a classical thing. Classically, everything's okay.
In quantum case, it is indeed anomalous.
Yeah, there's anomalous, so you have to cancel this anomaly by the infermions. So yeah, these are bosonic fields. They will have a.
So your fields are bosonic?
Yeah, my fields are bosonic. Yes, I mean I mentioned this. So as opposed to the usual formulation, yes, studies in the 70s, I kind of postulate that they are commuting because I want to get a commutative CPN model. This will be just a commutative CPN model.
порядке. Наверное, конечно, сейчас слышите, жуткие.
Yeah, the CPN models are also have been known since the 80s to be anomalous as quantum integrable models. And actually, you need fermions to cancel those anomalies as well. So,
Just now I mentioned just one general thing that bosonic systems of first order, they're much worse than fermionic systems of the first order. Because it's natural to write down this for fermions, but not for bosons.
well, yeah, maybe, well, not necessarily. I mean, it depends what systems you have. Like systems of ghosts, for example, they are of this type, yes, and so on. But I mean, it depends. In principle,
Well, I mean, if you speak about even surfaces, for example, yeah, then it's known that, say, for beta-gamma systems, which on normal surfaces, you have pathological formulas with some extra zeros or extra poles, if you wish. It's because of this zero move fixing, you acquire some extra problems.
I think you can always construct theories where all anomalies cancel and
No, you can, but
yes.
they are pathological in many respects. Maybe not for the purposes you need.
Yeah, I mean, it's yeah. So there are various questions about this. How various pathologies can be resolved. I agree with that, but in principle, of course, you can rewrite every bosonic system in some first-order formalism, and it will be fine, right? So it really depends on what kind of first-order formalism you're using. But the point, so far I'm just considering classical theory still. I just want to, what I want to do is I want to integrate out this V field. So the reason why we wanted to have this chiral symmetry and we wanted to prohibit U to the fourth and V to the fourth is that we want to integrate out either U or V. Well, they enter symmetrically, so it doesn't matter what you integrate out. So let's just integrate out V.
A small question. If I add the mass terms to this Lagrangian,
Yeah.
does all the symmetry still hold or not?
Well, no. Yeah, so no, mass terms, yes, they break chiral symmetry, so I really insist on chiral symmetry. So integrate out V.
No, but you can keep, for example, one of the, you can keep one, right?
Hmm?
You can add like chiral mass term, something like psi, projected psi.
Mm,
And then you'll have,
no, I don't think there is any way to add a chiral mass term. I mean, you can add UV.
well, for usually people add psi bar, and psi bar, gamma 3, gamma 5, psi bar.
Because you want to keep both.
No, you cannot keep
Yeah,
one,
but you can keep one, of course, yeah.
One.
And so you're just now using the fact that it's quadratic in each either U or V, and you can.
Yes. But somehow, finally, the quadratic form comes from the interaction. So there's a kappa, that's a coupling constant, yeah? So that's the inverse of the radius in sigma model language, yes. So Lagrangian becomes 1 over kappa, sum over so this is a radius squared, kind of, it stands here. And this is basically that's already a CPN model. There still is C star gauge symmetry, yes. So we can use C star to choose a partial gauge. So you could call it Hopf gauge, which is sum over equals 1. In this case, the denominator disappears, and we're left with a CPN model with a U1 gauge field. So this breaks C star down to U1. We're left with the usual formulation of the CPN model. So the basic idea, as compared to the usual formulation, is that there is no need to impose this gauge, and this condition is actually not a very good one, because this is what introduces these quadratic constraints. Here in this formulation, we don't have any constraints. In the Gross-Neveu formulation, we don't have any constraints. So we got rid somehow of the constraints by promoting the U1 symmetry to C star symmetry, which is also natural because, well, we know projective space is quotient of Cn by C star. So it's kind of natural to work in this. This is the procedure that shows that this is equivalent, at least classically, to the CPN model. But like I say, the idea is to work actually with this first order formulation, or this Gross-Neveu formulation. And one reason why it's nice to work with the Gross-Neveu formulation is that we can pick a better gauge than this Hopf gauge. Of course, there are different choices. Of course, you can go to inhomogeneous coordinates. You can set one of the u's to 1. But that breaks symmetry. That's maybe not the best gauge. Alternatively, there is a yet much better gauge, which is just to set the gauge field to 0. So in these models, the gauge field can be completely gauged away. And the reason is that, recall that the gauge transformation, so we're working on a plane now with decay conditions at infinity. So in this case, we can solve this equation by Cauchy-Green formula. Yeah, simply, just explicitly, which says that explicit solution. Yeah? There is a Cauchy kernel. If I act by d bar, get delta function here. This is the solution. So of course, the integral should converge for that to hold. So that means A decays at infinity sufficiently fast. Yeah, and in this gauge we get an ungauged Gross-Neveu model. So instead of imposing this gauge which introduces quadratic constraints into the theory, which makes it only kind of amenable to analysis in the 1/n expansion, we can use this gauge where A equals A bar equals 0 and simply construct, say, perturbation theory for this model, perturbation theory in kappa. That's a fine, well-defined perturbation theory. The grid functions are 1 over z, 1 over z bar. You can expand it. Of course, this is quantum mechanically. This is subject to anomaly cancellations, which should maybe mention. So the anomaly cancellation conditions are.
It was the same for A and bar.
Yeah. So A bar is the conjugate of A. So lambda is a complex number. There is a complex conjugate equation. This is in abelian, in abelian gauge theory. Yeah, non-abelian. So non-abelian, of course, in general, when we say path to Grassmannians, so we'll have non-abelian gauge groups, and that means that there will be a non-abelian equation here. It can be always be solved locally. can always be solved locally. And globally, you have intersections of some patches. Globally, you should.
We have a local system on
Yes, I mean, globally, this gauge field, it encodes a holomorphic vector bundle over your Riemann surface. And of course, the structure of vector bundle will, in general, play a role. So here I was only considering the case of C with decay conditions at infinity, so that it's a trivial bundle. But in general, like I said, the idea of placing this theory on the Riemann surface is that on the Riemann surface you will have 0 modes of the gauge fields remaining. This will parameterize moduli of holomorphic vector bundle of the surface, over the surface. And so this is kind of a formalism similar to string theory formalism, where in place of the metric you have a gauge field. So in string theory, string worldsheet theory, you integrate over a moduli space of complex structures or moduli spaces of metrics. Here you integrate over a moduli, in principle, you should integrate over moduli spaces of holomorphic vector bundles. And you can construct a similar, well, the genus expansion is replaced by expansion with respect to first term class of the bundle. So there is some general, here the first term class is 0 because the first term class is the integral of dA, and if A decays at infinity, it's 0. Yeah, so the idea is that on a, so the gauge field is topological. That is to say, the gauge field is topological. Actually, once you impose these complexified gauge transformations, there is no local gauge invariant that you can write. So for example, you cannot add to the Lagrangian trace f squared term, because f z bar is not gauge invariant. Under those transformations, it's shifted by I dt bar of log modulus of gamma or something like that.
You essentially have only one component of the gauge field, so you can't form FCZ bar.
No, I cannot form FZZ bar. FZZ bar is dZA Z bar. I mean, dZA minus dZA bar minus D bar A, dZ bar A.
But if you consider A without bar as a other component of the gauge field, the gauge transformations should be different. Both components should transform with the same function, but in your case, one component transforms with lambda, and the other one with lambda bar.
Exactly.
So it's not a gauge transformation in this sense. Or you
Yeah,
have only one half of the gauge field.
Yeah.
Whatever you choose.
Yeah. Okay, yes.
But may I ask, this gauge field, is it dynamical? Should I consider equations of motion, or it's external?
It's external field, yes, it's external field. Actually, it's auxiliary gauge field. No, I mean it's, sorry.
I mean, should I consider equations of motion?
Yes, you should consider, yeah.
But what are those equations, if I vary with respect to A?
Yes, so this is, A is an auxiliary gauge field, what it's called, yes? So,
Okay.
no, wait, let me just, so let's look first at this Lagrangian, yes? Here A enters quadratically. If you write an equation of motion, it's a linear equation for A. You place it back into the Lagrangian, you get the Fubini-Study metric here. So this is what is called this GLSL, yes, gauge linear sequential.
In the first Lagrangian, before you integrate it.
This one.
Yeah.
Yeah, it gives you a constraint that sum of dA UA is 0. This is actually a complex symplectic reduction, yes? So you have the U and V variables, they encode the complex symplectic from T star Cn, and then you do a complex symplectic reduction with respect to C star. This is the moment map constraint, and then we have an additional C star quotient. For example, you could, like I say, you could pick inhomogeneous coordinates, such as U n equals 1. And then you solve this for the respective momentum. So you write that Vn.
So C star acts in which direction? U or V?
On both, what, here. So so the complex symplectic form is DUA, DVA. It's preserved by this action.
But you have to exclude somehow.
Yes, some bad points, yes.
Yeah.
Yeah, so that's it. Just believe this is done. But I mean, so there's no respective real moment map constraint here, yes? But somehow u squared equals in the denominator here. So kind of that dynamically, the point u equals 0 is excluded, if you like, somehow. Yes. This is exactly related to nilpotent orbit thing, so resolution of nilpotent orbit. Yeah? So how does the nilpotent orbit come about? The interaction term here, this interaction term, can be written as a trace JJ bar, where J is a matrix. It's a kind of Kac-Moody current of the free system. Is U times V. It's a holomorphic variable. And you have the constraint says that its trace is 0, right? And now you see that J squared is 0.
More, it's rank 1.
Yeah. But I mean, J squared is 0. That's the relation to nilpotent orbits. So this J, and moreover, if you write out the equations of motion from the Lagrangian for J, you can write the equations for J, and you will find that the equation for J is precisely the principal chiral model equation of motion. I think it's a general property of such interactions, which are, J is the moment map of the corresponding complex symplectic form. And you have a coupling of trace JJ bar. You can call it moment map or current or whatever. But yes, so this is the equation of motion. So that's the relation to the first story. So this is the Lagrangian formulation of those reductions of principal chiral model, if you like. Okay, so now let's pass over to some other topics.
Before you come to other topics, so it's just a bit confused because you started with this principal chiral field and said that among the solutions to these models there are some of which correspond to reduced theories in a sense. Yeah? Now here you say that you accidentally you know that, or you can find in this non-direct way that if you start from just this Gross-Neveu CPN, Lagrangian, that would correspond to this simplest maybe or maximal contra reduction.
Yeah.
But it's kind of a piece of art. Yeah, you don't. It doesn't help you if you want to classify or find all Lagrangians for all possible reductions of principal chiral field. Or you do.
Yeah. So in principle, I don't insist on principal chiral field. I just took it as an example that people kind of are used to.
Yeah, but what is your aim? I mean, what would you like to?
No, the aim is to solve these models. For example, the CPN model, starting from this formulation. Yes.
And to solve, well, in classical or in quantum?
No, quantum case. Yes. So, for example, I will probably not have time to talk about this, but for example, one can develop perturbation theory in kappa. For example, one can compute a beta function of these theories quite consistently using this expansion. This has been done to, well, in supersymmetric case, I did it to 4 loops, and to 3 loops you find you have a 1 loop beta function, and at 2 and 3 loops you have no contribution, and at 4 loops you have something scheme dependent. But I mean, it's a well-defined perturbation theory.
Okay, that's a supersymmetric
Yes.
case.
Yes.
In non-supersymmetric you don't have even that, yeah?
Yeah.
So how does it help you? Okay, you have a relatively simple perturbation theory, as you say, with simple propagators. And so what? How does it help to solve it, and in what sense? When we speak about quantum theory, what means so full solution in a sense is if you find all correlation functions. Yeah? or
Well, I mean, it's
some-
far from that, but I guess some equations for the spectrum or something like that, yes.
Okay, perturbation theory, or exactly.
No, some kind of beta ansatz. One should write a beta ansatz starting from this Lagrange.
I see. But up to now, you didn't tell us how.
Yeah, I will not tell today, yes,
I see.
and the lack of time is not the only reason.
You just put the aim at least for today. What is your main message you want to demonstrate?
No, my main message is that there is this class of models that can have these Gross-Neveu formulations. These are exactly the models that correspond to resolutions of nilpotent orbits of classical groups.
But that, well, maybe because of my total list of any indication, I don't see by now any resolution of any orbit in
Yeah.
this model. Yeah. Can you tell us? And you said that that you in the introduction that you don't require a resolution.
Yes, yes, yes.
So вам не обязательно, чтобы был какой-то
Yes,
resolution.
yes.
So where it is here?
So here it's in this formulation, this U and V formulation. So the U and V formulation should be seen as a kind of quiver diagram where you have here C and you have Cn, and you have some map here, some map here. So one is U, the other is V. So the point is that in quivers, these arrows that go in two directions, you can put these two fields in one component of a Dirac speed. These are physically two components of the Dirac speed. And this is so associated to this quiver, you can write the corresponding hyperkähler quotient. And if the values of Fayet-Leopolds parameters are non-zero, this is a resolution. This is a smooth manifold. If the Fayet-Leopolds parameters are zero, this becomes the nilpotent orbit.
But here in this language you don't see this, yeah, because when you say about these Fayet-Leopolds parameters, the formation of this real moment conditions. Yeah.
Yeah,
That's right. Of that
That's right, yes. Yeah. Here we don't see it, yes. Here we don't see it, that's why I don't need resolutions. Yes? So here is, it's like ui squared minus vi squared equals zeta real, and then you have vi ui equals 0. This is the complex moment map that I have there. Yeah, so here zeta, depending on zeta positive or negative, I mean v and u switch roles and so on, so it doesn't really matter. But yeah, so for zeta non-zero, this is a cotangent bundle to CP1. This is the result manifold. I guess I should say CPN minus 1. CPN minus 1, yes. And you can write a smooth metric on this thing. This is the Iguchi-Hansen metric in the CP1 case, or in general case, some simple generalization thereof. In this Iguchi-Hansen metric, you have some sphere of size zeta. You can explicitly see it. And as zeta goes to 0, this is the kind of exceptional divisor, which shrinks to 0, and you get a nilpotent orbit. So nilpotent orbits are singular varieties.
The orbit is smooth. The closure.
Closure, yes. Yes, so resolutions of closures of nilpotent orbits, that's what I mean. How you relate it to flag varieties. So flag varieties, so in general for T star of arbitrary flag, UN flag here, there is also a corresponding quiver that you can write, which is Nakajima quiver, which has just more nodes. So this is Cn at the end, and here you have this CD1, CD2, etc. So in principle now it's clear how to generalize it, right? You just add more U and V fields. They interact with each other via gauge fields, but eventually you can actually set all of them to 0 by choice of gauge. And then you have this mu JJ bar thing at the end. So these models, if you write this like this is equivalent to these models I considered in 2014. So if you write it in geometric form. But Okay. Yeah, so there's some funny thing that for SO and SP cases,
Sorry,
Yes.
Just let ask the question and answered by some nonsense. So this CR, this real, you say that it's how to introduce it to the game. You say something about Fourier-Leopold, yeah, but that's in supersymmetric situation.
yeah.
But here for this model you cannot do this, right?
Yeah, you cannot do it, yeah. I mean, yes, this was the question, how you, so here zeta excludes the locus u equals 0 or v equals 0. And here it's excluded somehow by the fact that, well, in geometric setup, u squared appears in the denominator. So if you write it as a path integral, it's infinitely damped somehow, this configuration. So yeah, it does not appear. I mean, you just have to, actually, you should just think that these u and v are just some sections of some line bundles over your Riemann surface. So these are kind of linear variables. I think that's the right way to think about it. And somehow, in geometric form, this exceptional locus or whatever appears. But anyway, so the point is that actually, interesting thing is that in SO and SP cases, SO and SP cases, there are also quivers for nilpotent orbits. So there's this result of Kobach and so on. The nilpotent orbits can be written as hyperkähler quotients. They're hyperkähler, singular hyperkähler varieties, I mean closures. Singular hyperkähler varieties. There's some explicit quivers that you can write down. And therefore I can put it in this setup. But the resolved spaces are not hyperkähler quotients. Or at least are not known to be hyperkähler quotients.
Is a way to write down the Grosseu model. You already
Yes.
explained it, or it's obvious from what you said.
Yeah, I mean, it's so to every line, well, at least the quivers I have in mind correspond to nilpotent orbits. I mean, maybe in principle you could generalize it more, but so to every line there is a u and v variable, which belongs to, so say u belongs to, is a matrix from C di to C di plus 1. And v is an opposite matrix, transposed kind of. Then you write in the Gross-Neveu model in a straightforward way. The gauge fields are the gauge fields acting in the nodes. So these are GL di gauge fields. So these are GL nodes. And
But there you have only U1 in the left example.
yes, but there are two ways to look at it, right? Either as a simplicity quotient or a GAT quotient, yes. So here I'm talking about GAT quotient. So there is, I forget about the real moment map. And as was correctly pointed out, in principle I should be erasing first some unstable points and so on. So here I have all those quotients by complex groups, right? That was the idea, that the gauge field, the gauge symmetry is a complexification of it. So here I have C star here. In this node I have C star, if you like. Yeah, this condition fixes part of this C star. And so yeah, so there is for SO and SP you can write the quivers, but they don't admit Fourier-Laplace parameters. So here the Fourier-Laplace parameters come from the U1 part, C star part in this GLD. In SO and SP cases you don't have that U1 part, and therefore you don't have a Fourier-Laplace parameter. And therefore these manifolds are singular. I mean, these are closures of nilpotent orbits. But it doesn't matter from the point of view of this construction. You can integrate out the V's and so on, and you can just find out that you get the Grossmannians, SO and SP Grossmannians.
In the first example, you could have, disregarding the problem of Lagrangian, but from purely geometrical point of view, you could have written the holomorphic moment map equal to 1
Yeah.
instead of 0.
Yeah.
So you have a parameter also.
So the point here is that I think here you can always rotate it to 0 by an SU2 whatever R symmetry or something.
Once
I mean,
you
it's,
go
yes.
to the hyperkähler setting, then you can rotate.
Yes, yes. But here I cannot set it to, I cannot do this. Because in my case, this J, this VU is charged with respect to Lorentz group. So VU is a current. It's multiplied
On the worksheet, you mean?
on the worldsheet, yes. This is also the reason why I have nilpotent orbits, right? I cannot write a polynomial in J's. Because this will violate Lorentz invariance. What you're saying is you want me to add a kind of Fayet-Opolast term here, zeta A bar, plus zeta bar A. So this will do what you say, but this is not Lorentz invariant. On the contrary, you can do this in mechanics.
But who cares?
Oh, okay, I mean, yeah. So the point is that, yes, so somehow nilpotent orbits naturally arise in the Lorentz invariant situation, for one reason or another. But
Actually, the hyperkähler manifold is the same.
what does it mean?
You said if you can rotate it back or rotate it out or rotate it in, it's the same hyperkähler manifold.
Yes.
So if you put, forgetting the issue of Lorentz invariance, if you put one in the right hand side, what you get would be the coadjoint orbital of a regular element, right? And in such a way, the zero here is
Yes,
an orbital of the closure, resolution of the closure.
Yes.
But it is the same as a hyperkähler manifold. They are in the same family.
Oh, okay. I mean, yeah.
You have one parameter family of complex structures, right, on the hyperkähler. And for generic complex structure, the manifold looks like the orbit of the regular element. And for 2 points, on the level of examples, at some points, I guess at 2, it is a cotangent to the compact orbit. So it's the same manifold.
Okay, well, anyway, I mean, I don't have hyperkähler manifolds here anyway, right?
You don't want to see them.
I don't want to see them. I refuse to see them.
Вы же не перекелировали, а все. Ну, сейчас он сопроводит.
Какого касательно?
Это ты сажаешь ебучий канцер.
Да. Ну вот на таком примере будет так.
Yes, but what enters here is only the complex symplectic form, right? So I would say it's complex symplectic manifolds in general, right? Hyperkähler structure is probably there as well, but
No, I'm simply saying that it looks like you have possibility to view at the same problem from different perspectives. Breaking Lorentz invariant or keeping it looks like not very important. I mean, this священное правило не нарушает Лоренцову инверсию, похоже, здесь как-то не по делу. Я не знаю почему, я не знаю.
maybe. Yeah, no, there is a possibility to add this term naturally in mechanics. So in mechanics, if you do one-dimensional reduction of this is on the contrary very natural, right? You add a gauge field. And this will be a monopole gauge field on this. So all of these spaces, they have a natural line bond on them, whose first term class kind of is the flux of your monopole field in equostatic quantum mechanics. So I would say it's more natural to do this in quantum mechanics from my perspective. But,
Простите, я как пропустил, вы прямо вот так добавляете, то есть нарушает Gross's вариант.
but yes, but it's like Fayet-Opolast term, right? It shifts by derivative.
This, your parameters, they're just constants, yeah?
Yes, they're just constants, yes. Yes, in mechanics you can just do this, but you will find there's a quantization condition, right? Zeta has to be integer. I mean, it's a flux of some. So the wave functions are well defined and so on, but that's another story. So, yeah, in quantum mechanics you can do it, but somehow here I prefer not to do it. And moreover, like I say, as far as I know, for these resolutions of these nilpotent orbits, there is no quiver formulation. Oh, I mean, hyperkähler quotient formulation. But, okay, if you can give me some reference, yes, but I mean, metrics on these resolutions have been constructed by.
Disregarding the problem of Lagrange, but simply put, but you told us this when CR is not zero, but V times U is zero, it's a resolution of the closure.
Yeah, but I don't have this equation. I mean, I don't have this equation. No. Here, of course, there is a resolution.
Yeah.
I mean, for SO and
But
SP
if
cases.
you do GIT quotient, you will get the resolution, not the singular operator.
Well, mathematically, yes, but I mean, the question is what I get in what's the target space of my model? I mean, the target space of my model is anyway the exceptional divisor of the resolution.
This is not my
I don't know. But how do you see this? So you say that your target space is actually singular or what?
The phase space is singular.
Phase space is singular.
But once you integrate out the V variables, I can write exactly the same model for a given quiver.
As concerns the term phase space, I feel myself uneasy because the phase space in the two-dimensional sigma model is something infinite-dimensional. Okay?
Yes.
So you mean something different by saying phase
Yes,
space.
I mean exactly what is here. So I mean this phase space with V and U variables.
Фейс, потому что система первого порядка, поэтому это базично.
Yes.
Но она на фазовом пространстве принимает.
Yes, it's a subtle way to rigorously define. Doesn't matter. Yes, but in practical terms, I just have a system like this for a given quiver, which I can take from, for example, complex 1 for the nilpotent orbit. Then I can integrate out the V's and read out the metric of the U's. And then I compare it, I prove it that it's the metric on, say, SO and SP Grossmanians. And for resolved spaces, I think there's no hyperkähler quotient construction.
Even for the CPN, you say that when you integrate all this V, you get something like CPN, yeah? But then how exact is the statement? How do you see that original space is either singular or non-singular? How
No,
do you distinguish that?
No.
Not knowing anything about the field.
Yeah, so there is some general classification. So these closures of nilpotent orbits are complex symplectic singular varieties. And some of them admit complex symplectic resolutions. Some of them admit complex symplectic resolutions. If they admit complex symplectic resolutions, the resolution is always of the form T star of a flag manifold. So some theorem. So this is a resolution, okay? There is some nilpotent orbit closure. So the claim is that whenever a nilpotent orbit admits a resolution, it's like this. It's at least for SO, SP, and U classical cases, it's always a quiver. This is always a quiver gauge theory, if you like. I can write the corresponding model, and as a result, I get a sigma model with target space GC over P. The usual sigma model.
You mean the usual second order
Yes.
and derivatives. Relation.
So this is the kind of general statement.
Is B or field of result?
So yeah, it's usually with a B field.
Usually with.
Usually it is with a B field, unless it's a symmetric space. So for symmetric space there is a B field, but it's a topological.
Какой статус этого утверждения? Я так считаю, что то, что вы изначально говорите, это некоторые там математические теоремы.
Yes.
Есть какая-то там орбита нильпотентная, у нее есть резолюшн, там тра-та-та, тра-ля-ля.
Да.
Допустим, ну вот про Ничихамсона я, наверное, даже себе это немножко представляю.
Да.
Теперь какой статус этого утверждения в квантовой теории? Это что? Что это такое? Что это переполинование?
Нет, смотрите, во-первых, ну давайте я, может, по-русски отвечу, да? Значит, по этому соответствующему колчану, который известен, в принципе, хотя явно, я не знаю, ну, мы его явно написали, во всяком случае, когда нужно орбит. Вот. Можно написать Лагранжиан. Первого порядка. Затем исключить из него V-поля. Мы это сделали действительно не в полном обществе, мы это сделали, значит, для флагов.
Прям для уровня цитоида. Вот вы все это сделали, вы нам продемонстрировали.
Да. Это можно сделать во всех случаях.
Теперь только как вот отличить сингулярное от несингулярного на уровне тех манипуляций, которыми вы пользуетесь?
Значит, не, я думаю...
Этого, по-моему, я
думаю...
понимаю, Леша, по-моему,
Нет, я считаю, что это все не важно. То есть, как бы, UV — это просто линейные переменные, сечение линейных расслоений или комплексных расслоений, и теория возмущения хорошо определена, и ответы у вас будут согласовываться с ответами сигма-модели. Вот, как бы, и все, вот утверждение.
А с какими ответами?
Значит, с ответами, ну, много разных проверок, я просто не могу же как бы сразу все, да. То есть, например, мы вычисляли однопетлевые бета-функции, вот мы вычислили.
Сейчас еще простите, значит,
Да.
вы говорите про там, предложено, там есть какая-то наука про сигма-модель, вот кто-то знает, кто-то не знает.
Да.
И вы там, да, что-то там можно в теории возмущения проверять, все согласуется. Но как это вам дает ответ на вопрос, эта сигма-модель живет на сингулярном на чем-то или на несингулярном? Я этого уже не понимаю.
Нет, все не сингулярное. Таргет пространство — это однородное пространство, это как бы максимально не сингулярное, что может быть.
Нет, а вот это нилпотентная орбита, она тоже не сингулярная?
Нет, она сингулярная, но это не таргет пространство, это фазовое как бы пространство. Это пространство вот этих V у перемен.
Когда получится что-то не сингулярное, получится нормальная
Да, вы просто интегрируете по V переменным, по интегральному интеграле. После этого сингулярность исчезает.
Вы сказали, что вы что-то с чем-то сравниваете.
Да.
Вы можете в этом формулировке первого порядка что-то вычислить?
То, что
Второго порядка вы...
Да, например, смотрите, вот
говорили, что
да.
это получается вот обусек модель, кстати, там
не сингулярного всегда.
Да.
Там вы умеете за функцию вычислить, а здесь?
Да, здесь прекрасным образом
То есть
могу
вы отдельно можете там и там вычислить?
Да, могу и там вычислить, да. Но как обычно в сигмодели второго порядка, ну, используется какой-то метод фонового поля там и все такое. Здесь это ничего не нужно, мы просто, это как фи-4 теория. Изучаем диаграммы, тут диаграммы в однопетлевом приближении, вот две такие диаграммы вот есть. Вы суммируете там, как бы это чисто алгебра, тут, они обе логарифмически расходятся, получаете коэффициент, и, значит, мы показали, что ну, для СО, СП случая всегда вот это двойственное число как сетка, которое должно возникать, то есть второй Казимир, С2 в однопетлевом приближении. Ну, в случае СО, СП, там комбинаторика диаграмм чуть посложнее, то есть, потому что там вот эти токи, отображение моментов посложнее устроены. Вот. Кроме того, значит, в суперсимметричном случае, про который я, к сожалению, не успел рассказать, но он заключается в том, что вы должны супер как бы колчаны рассматривать, супер колчаны. И то есть у вас будет помимо бозонных полей еще фермионные поля. И вы выводите калибровочные суперполя.
Ну, сейчас суперсимметрично может быть.
Да, да.
Сейчас
Нет.
я что-то не понимаю, но если это Кемперов таргет. Нет, или таргет мы это звездочка отбрасываем.
Отбрасываем, да, отбрасываем. В этом как бы и смысл. То есть мы, да, вот это фазовое пространство, оно сингулярно, но фазовое пространство в кавычках, да, я согласен. Вот. Но известно, что это как просто общая некая теорема, я не переказал, значит, вот эти есть разрешения, это со звездочкой от пространств флагов, и дальше мы можем все привести к обычной сигма-модели с таким таргет пространством. Вот. Значит, в суперсимметричном случае, я говорю, я провел до 4 петель вот бета-функцию. В суперсимметричном случае что интересно, что есть утверждение, что бета-функция должна быть однопетлевой. И вот как бы хотелось бы получить это точное утверждение в этом формализме. Вот. Пока, вот я говорю, до 3 петель она проверена, что она однопетлевая. В 4-петлевом там возникают некие связанные со схемой перенормировки, в общем, сложности. Вообще, это все системы эти, это что такое? Это есть вот как бы действие, это есть возмущение конформной теории поля, типа бета-гамма-системы, таким оператором. Trace JJ bar. И вот интересно, что в суперсимметричном случае J это некий cut-smoothie ток.
Первую эту бета-гамма-систему нашли.
Да. Но в суперсимметричном случае вам еще нужно добавить свободный фермион, типа того. Да. Вот, значит, J это cut-smoothie ток, и оказывается, что в суперсимметричном случае это соответствует уровню 0. Как бы некая алгебра на уровне 0, вот она отвечает, вы точно так же можете просто избавиться от всех калибровочных полей, занулить их выбором калибровки, просто получать такую систему на уровне 0. И это соответствует world-shift суперсимметрии. Вот, и утверждение, значит, ну, есть даже гипотеза неких людей, там, Леклер и компания 20-летней давности про точную бета-функцию таких моделей. Она в этом случае на уровне 0 совпадает, то есть она тоже говорит, что однопетлевая бета-функция. Ну, вот как бы из четырехточечной функции это явно вычислить не очень просто. Вот. Значит, что еще было сделано в подтверждение всего этого? Значит, можно строить деформации этих моделей. Можно вместо trace JJ bar взять trace классическая R-матрица, действующая на J bar. Она зависит от параметра. Оказывается, это тоже интегрируемая модель, тоже есть представление нулевой кривизны. И можно посчитать
Матрица кого?
Билайна-Дринфельда.
Какой группы афины?
Ну, в смысле, это, как это называется, не динамическая, там... Нет, в смысле, там бывают всякие динамические, там, я имею в виду.
Параметр складывает очень.
Да, зависит от параметра. Да. Нет, группы GLM, там, SLM.
Дима, а складывает точки
Да, не
зрения.
зависит.
В смысле,
То
зависит.
есть конечномерная, не зависит. Я спросил, конечномерная или афинная?
Нет, ну как, ну в смысле, РС действует на РС, там, от Е и жидкое равняется S, там, Е и жидкое.
Леша, спектральный параметр? Где?
Здесь какой входит? Я не знаю, что это, я не могу сказать.
Вот это и меньше Ж, и больше Ж.
Нет, поиск прям.
То есть со спектральным параметром, да?
Ну вот она явно вот, как бы, выписывается.
Да.
Вот. И вы можете проверить бета-функцию для этого параметра S, однопетлевую. И показать, что он просто перенормируется как, то есть бета-функция равняется S точкой равняется NX. Это все делается вот просто вот с таких диаграмм. Тут свертки двух R-матриц, вы их вычисляете. То есть,
Все вы делаете вот в первом порядке.
А сейчас,
да.
А как многообразие?
Нет, а во втором порядке это вообще неизвестно как. Ну, то есть во втором порядке у вас очень сложная какая-то метрика возникает, деформированная. B-поле там деформированное. И ну, я проверял для случая там CP2, CP3, что стандартное уравнение бета-функции, которые пишутся через тензор Ричи, там, свертки H-полей, да, что они тоже удовлетворяются. Ну, это очень как бы сложно, а здесь все вот элементарно. Более того, вы можете доказать такое, ну, не знаю, смотря частично можно более-менее интересное утверждение, значит,
Сейчас за эту теорию с R-матрицей одна сверху выходит.
да, ну, в общем случае, да. Кроме CP1 случая. Да, в общем случае, содержится. Вот, например, вот есть такое, значит, утверждение, что, как я сказал, однопетлевая бета-функция пропорциональна двойственному числу Коксетера, то есть, например, она одинаковая для всех гроссманианов, GKN, и пропорциональна просто n. Однопетлевая бета-функция.
Когда что не течет?
Нет, здесь, да, тут, ну, как бы можно так перескалировать переменные, что течет только S. Да. Вот. Да, капа не течет. Да, но я хочу сказать, что для всех гроссманианов однопетлевая бета-функция пропорциональна n. Это связано с тем, что первый класс черных гроссманианов всегда пропорционален n. Не зависит от типа гроссманиана, ну от k как бы не зависит. Значит, вот. А оказывается, что можно это немножко обобщить на случай пространств флагов. Да, и это означает, что для всех гроссманианов есть, значит, тензор Ричи есть n умножить на метрику. Это вот однопетлевая, как бы, однопетлевая функция. И можно обобщить это на случай пространств флагов таким образом, что в случае пространств флагов, значит, метрика не единственна. Метрика, которая здесь возникает, это то, что называется редуктивная метрика или нормальная метрика. Она не Келлерова вообще-то. Вот. Поэтому...
В смысле, когда мы возвращаемся к формализму второго порядка.
Да. То есть тут как бы получается та метрика, в которой модель интегрируемая. И далеко не во всех метриках модель будет интегрируемая. Например, Келлеровая метрика, по всей видимости, отвечает неинтегрируемому
Ну,
модели.
это же народное пространство, да, правильно?
Нет, народные флаги, я про
Я
флаги.
имею в виду, метрика уже не обладает глобальной симметрией.
Не обладает. Да, целое семейство есть метрикс.
Потому что потом у вас левая симметрия всего остается.
Да, левая симметрия остается, да. Но можно доказать такое утверждение, что, значит, R и житая плюс 1/4 H и житая H и KL, H, G, GKL равняется N на J и житая. Да, H это производная Келлеровой, ну, как бы фундаментальной эрмитовой формы метрики.
Дифференциал B-поля. Или нет?
Да, дифференциал B-поля, да, правильно, да. Да. И в данном случае B-поле является Келлеровой формой метрики. То есть H есть D омега, где омега есть, ну, свертка метрики с комплект-структурой. Вот, в этом случае она не замкнута, потому что не келлеровая метрика. И вот есть такое обобщенное условие Эйнштейновости. Но это вот как бы правая часть уравнения бета-функции геометрической формулировки, и оттуда можно это вывести. Значит, первый класс членов пространств флагов, он уже более сложно выражается, он зависит от структуры флагов. Поэтому тут нет вот этого соответствия. Короче, вот это все следствие данной формулировки, которую можно получить.
Это уравнение без матрицы, да?
Да, это чисто для однородного случая, да. Для однородного.
Нет, это формула. Просто первая поправка.
Вот, короче говоря, вот, значит, в суперсимметричном случае это тоже очень естественная как бы формулировка, что фермионы живут в голоморфном касательном расслоении многообразия. И здесь есть такая как
Про суперсимметричный случай, может, нам надо отдельно будет еще.
Да, тоже можно.
Мы сейчас проведем какой-нибудь ликбез по
Суперсимметричном случае технически вы делаете в суперполях или?
Нет, без суперполей. Я делаю как фактор таргет пространства. То есть у меня будет фактор Cn/n по треугольной такой группе, которая есть лямбда 0 к си. Лямбда, вот это c со звездочкой, полупрямое произведение.
Жидкой суперсимметрии
Нет,
нет.
есть. В смысле, я стартую с модели с target space суперсимметрии. Ее суперкалибрую, и в результате получаю worldsheet суперсимметрию. А target space нет.
Одни переменные должны стать второго порядка, без первого, так выглядит, да?
Фермион остается первого порядка, а по V можно проинтегрировать. Да, то есть тут опять некая расширенная калибровочная симметрия, если ее зафиксировать определенным образом, возвращаемся в стандартную формулировку и проинтегрировать по V полям. Вот. Но это соответствует тому, что есть для касательных расслоений к гроссманианам есть такое утверждение, что это есть двойственное к тавтологическому расслоению помножить на фактор. В общем, есть такое геометрическое утверждение, как выразить касательное расслоение через тавтологическое расслоение. И это есть просто геометрическая реализация. Это как бы target space, такая реализация, а суперсимметрия в итоге worldsheet оказывается. Стандартная n равно 2,2 суперсимметрия. Но мы можем потом убить калибровочные поля и просто получить вот эту информацию JJ bar на уровне нормы. Вот. Надежда заключается в том, что это поможет дальше продвижению к решению этих моделей. Основная мысль такая.
Хорошо.
А вот идея матрицы, это необходимое условие для перенормирования, чтобы это R оператор был именно решение матрицы?
Не, это никто не изучал, собственно. Да,
А почему надо почему-то матрицу писать, а не что-нибудь еще?
Это как бы следует из-за...
Цели, так что это должно быть нормально.
Значит, там... Там есть некий ансатz, который принадлежит Костелло и Ямазаки, значит, с плоской связанности, которая пишется как-то типа там R U от J dz плюс там R U штрих от J с чертой dz с чертой. И если вы напишете условия плоскости этой связанности и воспользуетесь уравнением движения для J, вы получите классическое уравнение антибакста. Вот как бы. Это, в принципе, две строчки. Как бы.
Костелло и Ямазаки, это, наверное,
Да.
выше представление.
Я имею в виду весь их формализм. Тут не требуется их формализм 4D, там, тернсаймус или что. Вот в сухом остатке, что требуется, я вам рассказал.
Понятно. То есть, если мы определим такую связь, потребуем, чтобы она была плоская?
Да, плоская. Да, и дальше ты еще используешь уравнение движения для J, которые были уравнения главного керамного поля, а теперь они будут там J с R от J bar. То есть 2 раза R-матрица войдет. Поэтому, когда вы это сюда подставляете, получается квадратичное уравнение на R, которое есть классическое уравнение ангебакса. И там соотношение между параметрами там правильно возникает, что остается спектральный параметр. Вот. Вот так.
Ладно, спасибо.